Welcome back to Multivariate Calculus. In this video, we're going to be talking about extrema for functions of several variables. When we established the ideas of extrema for functions of a single variable, we were able to make some pretty quick observations based on the concavity of a function and the tangent line for the function. If I get my head out of the way and start drawing some pictures, we saw that in a function of a single variable, we had relative maximums occur when we had a tangent line that was horizontal and the concavity was downward. We had a relative minimum when you had a tangent line that was horizontal and the concavity was upward. We codified those things with the first derivative test and the second derivative test. For functions of several variables, we're going to have a lot of the same features appearing. We're going to have surfaces that are going to have maximums. It's going to be a dome that curves downward in every direction. And in order for there to be a peak, there has to be a place where both the x direction and the y direction are turning around. It's a lot harder to draw. I'm not even going to try. But we know that there's going to be a horizontal tangent plane and we need some analog for concave down. If it is concave down in the x direction and also concave down in the y direction, then we should be in good shape. And that will give us a local maximum. We can also have the opposite picture. If we have a bowl shape in every direction, then we want a horizontal tangent plane and we want to be concave up in every direction. The trick that we're going to run into, we found in functions of a single variable that very often a point of inflection, a place where the concavity changed, could result in an undefined tangent line, or it could result in a horizontal tangent line. Right? A classic example there is a cubic function. In the cubic function, you've got this point in the middle that is a horizontal tangent line, and it makes a lot more sense when I don't have my head in the way of the drawing. All right, so that's something that we saw in functions of a single variable. And that's something that's going to be even worse in functions of several variables because saddle points are fairly common. Right? We talked about the hyperbolic paraboloid, which curls upward in one direction and curls downward in the opposite direction. So if you look just at the x direction, it looks like it's a relative minimum. And if you look in the y direction, it looks like it's a relative maximum. And so we need to be a little bit more discerning. To make things even worse, we can take that saddle shape and we can rotate it in the xy plane. So the direction of maximum might be along the line y equals 2x, and the direction of local minimum might be in the line y equals negative 1/3 x, just to make a mess of everything. All right. So tangent planes being horizontal is fairly straightforward. We don't have to go so far as to even write the equation of the tangent plane, because when a tangent plane is horizontal, that's the same thing as the normal vector being vertical. So we're looking for a normal vector in the form of 0, 0, and some constant k. thinking about that and breaking it down a little bit further, we're looking for a place where the partial of big F with respect to x is 0, and the partial of big F with respect to y is 0. And if we think back to writing big F of x, y, and z as z minus little f of x, y, and defining our surface as the level curve of the three-dimensional function when w is equal to 0, well, using the properties of partial derivatives, if partial f partial x equals 0, that implies that partial little f partial x is equal to 0, and similarly partial little f partial y is equal to 0. All right, the first derivative test extends into two dimensions pretty well exactly how you would think it would. We need places where the derivative is equal to 0. The derivative is two-dimensional, so we need the two-dimensional derivative to be equal to 0, but we still just need the derivative to be equal to 0. For the second derivative, for the concavity, because of all the mess we have, we're going to need to try to make things a little bit less messy. And in order to do that, we are going to turn to matrices and the determinant of a matrix. Just like we saw with the cross product, you don't have to use a matrix to set this up, but it does seem to make things a little bit easier. And we're just going to set up a derivative matrix where we're going to take, actually, let's call this thing capital D. We're going to set up capital D where we're going to take the partial derivative with respect to x twice in the first row, first column. We're going to set up the partial derivative where we take the derivative with respect to x and then y. We're going to set up taking the derivative with respect to y then x. And we're going to set up taking with respect to y twice. And it's going to give us a 2 by 2 matrix, and we're going to find the determinant of that matrix. We call that matrix D. It is an operator. It tells us something to do on each of these 4 entries to the function. So most textbooks don't give this formula. They give 3 steps further along in the process. And if you aren't comfortable working with matrices and determinants, it's perfectly fine to learn that formula. But if you have gotten used to thinking about the determinant of a matrix from all the cross products that we have done, then you can look at this one, and it's a lot easier to understand what's happening. As you go across or you go down, in the first row, we're differentiating with respect to x. In the second row, we're differentiating with respect to y. In the first column, we're differentiating with respect to x. In the second column, we're differentiating with respect to y. Right? So x, y. And then in the rows, x, y. So x and x and y and x, y and y. And again, y and x and y, it's the same thing because we have Clairaut's theorem. We don't have to worry about that breaking. If the derivatives weren't continuous, then we'd have something to worry about, but there are no practical applications of that. So unless you're going onward to study further mathematics, we don't have to worry about it, and those 2 partial derivatives are just going to be equal to each other. All right, so that mnemonic of just thinking about x then y, and setting up and getting the 4 entries here, telling you which order to take the partial derivatives, will give us the tools we need. So if I have a particular function, I can write this as df is going to be the partial derivative set up in this order, and then I can take the determinant by multiplying the main diagonal, multiplying the off diagonal, and subtracting them. And again, because Clairaut's theorem, partial with respect to x, then y, partial with respect to y, then x, it's the same thing. We can do it all at once. All right, so for example, I might ask us to find any extrema for the function z equals negative x cubed plus 4xy minus 2y squared plus 1. You can graph this surface in order to get some understanding of what the extrema are going to look like. That's not something I'm too worried about right now. So instead, I'm just going to dive right into taking some derivatives. We are going to need the derivative with respect to x, which is going to be negative 3x squared plus 4y. And we're going to need the derivative with respect to y, which is going to be 4x minus 4y. And we set both of those things equal to 0, and we get a system of two equations with two unknowns. It's a little bit messy. It's a nonlinear system of two equations with two unknowns, but it is still a fairly straightforward system. In fact, this one's really nice because if I just add them together, I get an equation that has just x, giving me the solutions x equals 0 or x equals 4/3. Then, taking these results and plugging them back into one of the equations, I think the second equation is a little bit easier to work with. I'm going to get when x is 0, that means that y is 0. And when x is 4/3, I get 16/3 minus 4y equals 0, which means that 4y equals 16/3, and y is positive 4/3. So I get 4/3, 4/3 as, excuse me, I get 4/3, 4/3 as my second critical point. So these 2 points are the places where the function might be an extreme value. And in order to figure out whether it is a maximum or a minimum, again, you can always graph the surface. That certainly does work when you have a computer available. But when you don't have a computer available, we're going to take that determinant of that matrix, which means we're going to need all of the second derivatives. So we're going to need the second derivative of z with respect to x, which is going to be minus 6x. We're going to need the mixed second partial derivative. We can either take this and differentiate with respect to y, or this and differentiate with respect to x. Either way, we get 4. And then we're going to need the second partial with respect to y. Means take that second equation, differentiate with respect to y, and we get negative 4. All right, so with that in hand, we are looking at the determinant of this 2 by 2 matrix. Normally, my next step would be to plug in the values of x and y, but this one's not too bad, so I'm just going to keep going. If these were nasty, I would plug in values of x and y now and then take the determinant multiple times, but this is pretty straightforward. I just get 24x minus 16. And so I can plug in. When x equals 0, that means that d is negative 16. And when x is 4/3 and y is 4/3, that means that d is going to be, well, 24 divided by 3 is 8. 8 times 4 is 32. 32 minus 16 is positive 16. But the only thing that really matters is that the first one is negative and the second one is positive. When this thing comes out negative, we're going to end up with a saddle point. When this thing comes out positive, we're going to end up with an extrema. And once we know we have an extrema, we can go back and think about the derivatives with respect to x and y. The single direction derivatives, we have a negative here. You also have a negative if you put in the value of x there. It's the same sign, both positive and both negative. That should always happen, right? This thing can only be positive if the second with respect to x and the second partial with respect to y are the same sign. In this case, they are both negative, and so we use the same result that we had with the second derivative test for a function of a single variable. Concave downward, negative second partial meant a local maximum. Concave upward, positive second partial meant a local minimum. If it turns out that d is equal to 0, then we get nothing. So negative saddle point, positive, we get extrema. And so we have one maximum at the point 4/3, 4/3. We have a saddle at the origin. There are no local minimums. All right. I would like you to look at this function. F of x and y is equal to 2x squared plus y squared plus 8x minus 6y plus 15. Use the first derivative test to classify any relative extrema, and then use the second derivative test to determine whether those extrema are local maximums, local minimums, or saddle points, or if the second derivative test is inconclusive, you can report that. All right, take a few minutes, see what you can come up with on that problem, and I'll see you in the next video.